Okay, let's talk about using proportions to solve problems. This is section 6.2. And we have properties, different properties of proportions. And what that means is that there's different ways for us to write proportions and still have them be equal to where we can solve using cross multiplication. And the first one is called the cross product property. Cross product property says if I have a ratio of A to A over B, and it equals C over D, where B and D both cannot equal 0, and that's because they're in the denominator of a fraction. Remember that we can't divide by 0. Then we know that if we cross multiply, AD is going to equal BC. So A times D is going to equal B times C. Yeah. Okay. Now the reciprocal property says that I can flip both of those over. If I have A over B equals C over D again, then an equivalent property would be that B over A, that ratio, is going to equal D over C. So if I flip one of them over, I have to flip the other one over, but they're still equal proportion. The third property of proportions, and then we kind of run out of names, so this is just the third property. If A over B equals C over D, then I can write A over C, so I can take the numerators on both, A over C, that ratio, and it'll be equal to the ratio of B over D, the denominators. Okay? The fourth property, and this is one that you will see, you will need to see it, understand it, but we don't use it a whole lot. It says if I have two ratios, A over B, and it equals C over D, then I can add the denominators. If you look here, the denominators, I can add the denominator, A plus B over B, and that will be in the same ratio as C plus D over D. So we add the denominators to both of the numerators, and then that is still an equal ratio, an equal proportion. So let's look at example 1 here in this diagram. We know that MN over RS, so between the two triangles, we know MN over RS, that ratio, will be in the exact same ratio as NP over ST. So let's write, first of all, if you look at A here, this is the first section, we're going to write 4 true proportions. So let's look at what would those proportions be. Well, the first one's going to be that, and I will write A here, is that MN over RS is going to equal NP over ST. Okay, so that's one of the first proportions. We know that one's true. That's your cross product property. The second one says that we can use the reciprocal. We can flip them both over, and that would be RS over MN, the ratio of those two sides, would be equal to ST over NP. So if we flip both of them over, we have a true proportion. So there's our first one. There's our second one. Here's our third one. So this proportion would be, and let's look at the third property of proportions. It says if I take both of the numerators, so I can write MN over NP, okay, the ratio of the two numerators from the first statement, and that's going to equal the ratio of RS over ST. Still a congruent, or I'm sorry, not congruent, an equal ratio, equal, being an equal proportion. And then the fourth one is that one that we do need to know, so make sure you know it. That would say I have MN plus the denominator, RS, over RS. That ratio is going to equal the ratio of NP plus ST, the denominator, over ST, the denominator. And so those are your 4 true proportions that we would get. Okay, now for part B. I'm going to go up here. I'm sorry I didn't leave myself enough room, and solve for x, because that's the last part of example 1. We're going to solve for x. So let's just use the proportion, the first one that we set up, we know the cross product property, where MN I'm going to use the very first one here. MN, which is 8, over RS, which is 10. So the ratio of those two sides is going to equal the ratio of NP, which is 4, over X. That's the ST. And so then cross product property says that we would cross multiply. So 8 times X, which is 8X, is going to equal 4 times 10, 40. And then when I solve, I'm going to get X equals 5. So there's my solving for X. Now, if you go through and look at the book and look at all the examples, and it's a good idea when we go through these sections to still go through the sections in the book and read them. There's usually a couple of other examples that'll help you get the idea if you're not quite sure when we get finished. But let's look at example 2. In this diagram, it says that BD over DA, the ratio of BD, right here, over DA, the ratio of those two pieces are in the same ratio as BE over here over EC. So those are going to be the same ratio. That will give us an equal proportion and help us solve. Now, if you look in the book, it's going to have you use that fourth property proportion. I like to do it a little bit differently. And I'm going to look at BD, and let's try to figure out how would I represent this side right here, BD. I don't know its measure, right? I know from B to A, the whole entire left side is X, and DA is 3. So let's represent BD by X minus 3. So that's going to be my measurement for BD. And so I'm going to go back to using the cross product property. Whenever I can, that's my favorite. So we're going to look at BD, and I'm going to write down, that's my X minus 3. We just figured that. Over DA. So that ratio is going to be equal to the ratio of sides BE, which we have 18, over that little piece at the bottom, EC, which is 6. And so now I'm going to cross multiply. Know that when you have more than one term up here, use a different color. When you have more than one term in one, either your denominator or numerator, it doesn't matter. You need to put that in parentheses, because that's going to be a 6 times X minus 3 in parentheses, and know that you have to distribute that. And then 3 times 18. So I'm going to get 6X minus 18, and then 3 times 18 is 54. So now when I add 18 to the other side, I'm going to get 6X equals 72. And so my X equals 12. Now, that is, what are we looking for? Here's what we needed to find, BA and BD. So BA is X. And if you look at that, that's the whole thing from B to A, and that was my X value. So BA is 12. And then I want BD. Well, I find BD by taking the whole side, 12, and subtracting the 3 at the bottom. Remember, we represented BD by that measure right there, X minus 3. And so 12 minus 3 is going to give me 9. And so BD is 9. All right, so let's talk about a scale. Scale is a ratio that's going to describe how the dimensions in a scale drawing are related to the actual dimensions of an object. And so you'll see more about that on page 365. But here's an example, a blueprint which shows a scale drawing of a cell phone. The length of the antenna on the blueprint is 5 centimeters, when the actual length of the antenna is 2 centimeters. So what is the scale that the blueprint's using? So let's do the blueprint, remember these are in ratio, over the antenna, and I'm just going to abbreviate the BP for blueprint, over the antenna. So the scale is going to be a ratio. The blueprint is 5 centimeters, and the antenna's actual measure is 2 centimeters. And so if we did divide this, the 5 divided by 2, let's divide the top and the bottom by 2, I'm going to get 2.5 to 1. So that's the scale. The scale is a ratio, and that would be the ratio right there, 2.5 to 1. Okay, so now we're on to 6.6, which is triangle proportionality theorems. So we have some theorems here, and that's why we go ahead and present these at the beginning. Here's our first theorem, the triangle proportionality theorem. So if I have two parallel sides here, TU is parallel to QS, then I know that the two sides are in the same proportion. So the ratio of RT over TQ, RT over TQ, that ratio would be in the exact same ratio as RU over US. And so those sides are proportional. And this is what it said. This is your picture. But it says if the proportionality theorem, if you go read them, if a line intersecting a triangle, so we have a triangle, RQS, and this line intersecting it, if it's parallel to one of the sides of a triangle, then it will automatically divide the sides proportionally. And so that's going to be an important theorem for us to know. If we have a triangle and one side is parallel to that line that intersects your triangle, your sides are divided proportionally. So the converse triangle proportionality theorem just says that if I have two sides in a triangle and there's an intersecting line, if I have the sides RT over TQ would be equal to RU over US. If they're in the same proportion, then you must have parallel lines. And so that's that converse that we can use to prove parallel lines. So for example 1, what is the length of RQ? So we want to look at, here's my parallel lines in this one triangle. So I know my sides are divided proportionally, which would mean that RQ over QU, I'm going to use RQ, and that's what we don't know, over QU, which is 9, is going to be in the same proportion as RS, which is 4, over ST, which is 6. And so RQ there is my variable. I'm going to use it as one term. So I'll put it together so we know that's what I'm solving for right there. RQ times 6 is going to equal 4 times 9, which is 36. So when I divide both sides by that 6 right here, then I know RQ, which is what I'm solving for, is going to equal 6. And so that's RQ. That's how we figure out what that length will be. Let's look at example number 2. Now, example number 2, I'm determining if I have parallel lines. And so to figure out if I have parallel lines, knowing that I have this line that is parallel to the third side here, we hope. I actually should not have drawn on the little triangles yet because we don't know if they're parallel yet. So let's figure that out. If they're going to be parallel, then my sides are proportional. And so that would have to mean that 90 over 50, RS over ST, would have to be in the exact proportion of 72 over 40. Now there are two ways we can do this. We can either simplify each ratio on each side and see if we get the same ratio. And as long as the ratios are equal in simplified form, then we have parallel lines. And the other way that you can do it is to cross multiply. So I would do 90 times 40 and see if that equals 50 times 72. And if it's equal, then they are in the same proportion. So first, I would simplify this. 90 over 50 is going to simplify to 9 over 5. And if you aren't sure on a calculator how to simplify a fraction, 72 over 40, if I want to get that in lowest fraction form, you're going to hit your math button on the left-hand side of your calculator, hit math, enter, enter, and that'll give you this fraction right here in lowest form. and you will get 9/5. And so therefore I know that PS is parallel to QR. Okay? Okay, theorem 6.6, and these are you'll find on page 398. If we have three parallel lines, so here's my three parallel lines, R, S, and T, and if they intersect two transversals, so L and M here would be my transversals, then they divide the transversals proportionally. So the pieces of the transversal here, W over Y, I'm sorry, UW, this section right here is UW, and then W to Y right here. That ratio, UW to WY, is going to be in the same ratio to VX over XZ. So those pieces will be in the same ratio. That will give us an equal proportion. And so, for example, we want to find the length of AB right here. We're looking for that length X. So first I'd be asking you, do you know if you have three parallel lines? Can we tell if those three lines right there are parallel? And hopefully you guys would look and see that I have right angles. And so if I have a line that's perpendicular to a transversal, to a line, then if each of these lines is perpendicular to the same line, then that makes them parallel to each other. And so yes, we do have three parallel lines, so we can set up our proportion. That would mean 16 over x is going to be in the same ratio. So the first one over the second one, 16 over x, is going to be in the same ratio as 15 over 8. I'm sorry, 18. I said 8, I meant 18. And so here we're going to cross multiply. I'm going to do 15 times x, so 15x is going to be in the same, or equal to 16 times 18. And 16 times 18 is 288. Now we divide both sides by 15. And my x equals, let's divide by 15, 19.2. And so that side, 19.2, that piece x has to be 19.2 for those to be equal ratios and be in the same proportion. Okay, the last theorem, 6.7. If a ray, so my ray here is CD, and remember how we draw that. My ray bisects an angle of a triangle. So we have a triangle, it's bisecting angle C. So I'm going to get two other angles here. Then it will divide the opposite sides from the angle here that we're bisecting. It's going to divide the opposite sides into segments whose lengths are proportional to the lengths of the other two sides. And so that would mean this piece AD over DB, those two segments, the ratio of those two segments is going to equal the ratio of side CA here over CB. So it'll be in the same ratio as the two sides. So remember, it has to be, let me use blue for this one, AD on the top and CA on the top of the other one. Those will be, and DB on the bottom of the first ratio and CB on the bottom of the second ratio. Now remember, we talked about the different ways that we can write this though. I can flip it over and write DB over AD, and that will be equal to the ratio of CB over CA. And I can also do, remember the third one said I can write AD over CA, and it'll be equal to the ratio of DB over CB. So we could also do that one also. Just keep that in mind, that there's different ways to write these ratios and still get a true equal proportion. All right, so let's find the length of AB in the example. Okay, I apologize. I had a different picture before and I changed my mind. I liked this problem better. We're going to find the length of RS. Sorry about that. We are finding the length of RS. And so the other thing you will need to know in the picture that didn't get put in is that these two angles are congruent. QPR and RPS are congruent angles. And so if they are congruent, then that means PR, that segment, is an angle bisector. It has bisected QPS. And so since it is bisected, then I know that the segments on the opposite side, QR, let's write it out first, QR over RS, that ratio, is going to be equal to the ratio of the sides. So I want to, since I started with QR on the top, then I need to do that corresponding, that segment that touches it, that of the triangle, PQ over PS. And so that would give me a true proportion, a equal proportion. So QR, we don't know, do we? So that's going to be one of those problems, just like that first example we looked at, where we have to figure out, how do I represent QR? Well, we know the whole side, QS, is 15. And then if I subtract X, I'm going to get this piece that's left, QR. And so that's how we're going to represent QR. 15 minus the X at the bottom over RS, which is my X, is in the same ratio of 7, and that's QP, over PS, which is 13. Again, remember to put this top one in parentheses. We have to distribute that. So I'm going to get 13 times 15. Tell you what, I'm going to start with the other one first. So I'm going to start here, X times 7. So I'm going to get 7X equals, now I'm going to do 13 times 15, which is 195. And then minus 13 times the X, so that's 13X. Now I'm going to add 13X to the left side, which is going to give me 20X here, equals 195. And divide both sides by 20. My X is going to be 9.75. Okay, and that would be the length of RS. Then if I'm talking length, I don't need the bar. Okay, the measure of RS is 9.75. All right, and that is section 6.6. See you next time.